Welcome back to another Explainer. I am absolutely pumped about our topic today because, well, we're going to completely decode the inner workings of computers. We're going on this massive journey, traveling from the raw, tangible physical hardware all the way up to the abstract, human-driven logic that literally powers our entire digital world. If you've ever found yourself wondering how a bunch of silicon and wire actually solves problems, you are exactly where you need to be.
Okay, to kick things off, I want you to consider this quote. Memory is essentially the human brain of the computer. Really think about that for a second. Just like your own brain holds on to your childhood memories, your current thoughts, and even the subconscious instructions for how to, say, tie your shoes, computer memory does the exact same thing. It holds the data and the instructions for absolutely everything the machine does. It's the foundational space where all processing actually begins.
So, here's our game plan for today. We'll start with the hardware engine, specifically memory and the CPU. Then we'll look at the ultimate manager, which is the operating system. After that, we'll dive into the translators, like compilers and linkers. And finally, we'll wrap up with the blueprint, looking at algorithms and flowcharts.
All right, let's jump straight into part one, the hardware engine, focusing on memory and the CPU.
When we look at the physical components that store our information, it is honestly mind-blowing how they scale up. Whether you're saving a tiny little text file or firing up a massive, graphically intense video game, every single piece of that data starts at the very top of this scale as a bit, the absolute smallest unit, just a simple 0 or 1. From there, we just start grouping them. 4 bits make a nibble. Yep, in nibble, 8 bits make a byte. And as you go down the list, you'll see this magical multiplier pop up, 1024. A kilobyte is 1024 bytes. A megabyte is 1,024 kilobytes, cascading all the way down to those enormous petabytes. So every massive digital scale you interact with is built entirely on these tiny binary foundations.
Now, let's talk about the real brains of the operation, the CPU. The CPU isn't just one big monolithic blob. It's actually divided into 3 highly specialized departments working perfectly in sync. You've got the arithmetic logic unit, the control unit, and the memory unit. The control unit is basically the traffic cop, managing the flow of data and instructions. The memory unit handles immediate storage, meaning it's quickly grabbing exactly what the CPU needs right this very second. But we really need to look a bit closer at that first one, the ALU.
Understanding the arithmetic logic unit, or ALU, is absolutely crucial. Seriously, if you're taking any computer science exams, this is going to show up. The ALU is split into 2 halves. You have the arithmetic section for all your math, so addition, subtraction, multiplication, and then the logic section. The logic section handles decision-making, like comparing 2 numbers to figure out which one is larger, or merging different data sets. Whenever you ask your computer to calculate something, even something as simple as 10 plus 20, the ALU is where that magic actually happens.
But you know, this brings up a pretty massive question. We've got all these raw hardware components, right? We've got memory cells storing bits, the ALU just waiting around to do some math, the control unit on standby. But how do these chaotic, individual pieces of hardware actually get organized into a functional, user-friendly machine? Like, who is directing the traffic from a macro level?
Well, that brings us to part 2, the ultimate manager, better known as the operating system. Look, without an operating system, or OS, your expensive computer is basically just a glowing paperweight. The OS is the vital software interface that acts as a bridge. Think about it like this. When you want to save a photo, you, the user, click a Save button in your app. But it's the operating system that actually goes and talks to the hardware, finds the empty space on your physical hard drive, and physically writes that data. It connects what you want to do with the physical hardware's capability to actually do it.
So, the OS handles a ton of daily chores. It manages processes, constantly deciding which app gets CPU time. It manages memory, allocating RAM, so having too many browser tabs open doesn't just crash your whole system. It also handles file management and security. But I want you to look at that third point, device management. Here's a real-world example. When you first turn your computer on, you've probably noticed the lights on your keyboard or mouse flash for a quick second, right? That is the operating system actively testing your input and output devices, just making sure everything is connected and working before the system fully boots up. It is constantly checking on the hardware.
Okay, so we have the hardware, and we have an OS to manage it. But we hit another huge roadblock. You and I, we write programs in human-readable code. We use English words like print or if. But as we already established, the machine itself only understands zeros and ones. So how in the world does the machine understand us?
That perfectly transitions us to part 3, the translators. We're talking compilers, interpreters, linkers, and loaders.
Distinguishing between these system tools is a total cornerstone for understanding how software actually runs. Let's compare our main translators. A compiler takes your entire program and reads the whole thing, like a book from cover to cover, and translates it into machine code in one single massive run. Because of that, it's incredibly fast when you actually run the program, which is why performance-heavy languages like C and C++ use it. An interpreter, on the other hand, reads and translates your code sentence by sentence, line by line. It is a bit slower, sure, but is highly flexible. If it hits an error, it stops immediately and tells you exactly where you messed up. Languages like Python rely heavily on interpreters.
Then we have 2 more essential tools, the linker and the loader. You see, once your code is translated, it's very often broken up into separate pieces. The linker's job is exactly what it sounds like. It merges these multiple files together into one single executable program. Imagine you have a file that calculates variable A and a totally separate one for variable B. The linker stitches them together. After that, the loader steps in. The loader takes that newly stitched executable file and literally loads it directly into the computer's active memory, the RAM, so the CPU can finally get to work and execute it. So it's link and then load.
And finally, we arrive at part 4, the blueprint, algorithms, flowcharts, and pseudocode.
Long before any code is ever typed out or translated, we humans have to do the planning. Everything starts with an algorithm. An algorithm is just a specific, finite sequence of well-defined steps required to solve a particular problem and produce an output. The absolutely critical words here are finite and well-defined. You see, an algorithm isn't just a vague suggestion. It must have a defined input, a crystal-clear sequence of operations, and a guaranteed endpoint that gives you an output.
Let's actually look at how a human thought process maps onto this. Here is a super simple algorithm for adding 2 numbers. Step 1, we read our inputs. Let's just say A is 10 and B is 20. Step 2, we create a container, basically a variable, and we'll call it sum to hold our answer. Step 3, we actually do the calculation, so sum equals A plus B. And step 4, we print the final sum, which is 30. It's incredibly clear, it's step-by-step, and it has a definitive finish line. This is the raw logic that eventually guides the code.
Now, developers don't usually just write these steps out in plain text. We like to visualize them. We use flowcharts, which rely on specific graphical shapes, ovals for starting and stopping, parallelograms for inputs, to physically draw out the algorithm. Or, alternatively, we use pseudocode. Pseudocode is kind of cool because it's not an official programming language like C++ or Python. It's more like a hybrid intermediate draft made up of plain English and programming logic. It basically lets developers map out their if this, then that structure without having to stress over getting the syntax perfectly right.
Which really leaves us with this final thought to ponder. Isn't it absolutely amazing that the incredibly complex digital world we live in, literally everything from the apps on your phone to global financial networks, is entirely built on this exact foundation? I mean, it's all just layers. It starts with simple human algorithms drafted in pseudocode, which are then translated by compilers, managed by complex operating systems, and ultimately executed by a tiny physical CPU calculating nothing but zeros and ones. It is a wild journey from hardware to logic. Thanks so much for joining me on this explainer. Keep learning, keep questioning, and I will catch you on the next deep dive.